Okay, so we start our session. We're starting at the Stephen Case textbook, volume one. So it's volume uh, one, uh, estimation theory. So we have talked about detection theory. Now we move to uh, estimation, and we are going to start at chapter one. Okay. Uh, so, uh, so the estimation in has applications in many different areas, and particularly in communications and signal processing. So it has applications including radar, sonar, speech, and image and biomedical communication control seismology, so on and so forth. And all those problems share the common need for estimate uh, for estimate the values of a group of parameters. So I think this is the key point for the estimation theory. So when we talk about this estimation, when we talk about estimate, it's related to uh, the estimation for a parameter theta, or it could be a group of parameters. It's either a single parameter or a group of parameters. Okay, so um, we will describe some of the examples and some of the mathematics and signal models before moving to the details. So, for example, in radar, we are interested in determining the position, or we will say the range R of an aircraft. So we will transmit an electromagnetic pulse that is reflected by the aircraft, then causing an echo to be received by antenna. Uh, this uh, for some seconds later. Then we will determine the range by tau zero equal to 2r divided by speed of light c. Okay, so let's see the, the graph. Uh, the radar the radar is trying to estimate a target aircraft, and so that is uh, the range of between the radar and the target, and it sends out the electromagnetic wave, and then it gets refracted back to the radar, and it's going to estimate that range r. So that r will be the parameter to be estimated. So if we look at the time domain, it's transmitting a signal. For example, this sinusoidal wave. Then its received wave will be for some time later, tau zero later, it gets refracted back. It gets refracted back. Then you may wonder how come this well-behaved continuous wave will get this kind of shape that is slightly different than the sinusoidal wave. So what happens is when you transmit a signal into the space and gets reflected back, it might be disturbed by some kind of noise. Therefore, the waveform different will be different from the transmit signal, and then the received signal. It will be slightly different because there are noises. And then for those part that has no signal, it still has some disturbance, that is the noise. So there's always the noise that will influence our determination for the tau zero. So it's not as well shaped like this. You have a starting point and an ending point, that kind of thing. So the starting point and the ending point may not be that clear anymore. So that causes the difference between uh, this waveform and that waveform, and it also gives you deviations in terms of determining the tau zero. Okay, so yeah, so in other words, we are going to determine the parameter of our interest for a time series. And another common application is the sonar, in which we are also interested in the position of the target, such as a submarine. And as you can see, this is a very important application. A typical sonar is shown in the figure. And so let's see. Uh, you have a ship that is uh, giving out a towed array. Array meaning that you have multiple elements inside. You have multiple elements inside the array. And then this is the target. And then it generates some kind of signals. For example, if it's moving, then it's disturbing the waveform in the water. And the waveform in the water gets received by the tow array. So there could be sensor 1, sensor 2, and sensor 3. And then you get sensor 1 output some kind of wave. And then sensor 2 gives you some kind of wave. And you are trying to estimate the time difference, which is the tau zero between the sensors. Okay, so by measuring the tau zero, the delay between sensors, we determine the bearing beta from the expression, and this is from the triangular structure, the triangular structure of the array. So, for example, you have this, and then it gets transmitted wave comes in like this, and then you have some kind of triangular structure in that array, and versus the angle of arrival for the incoming signal. And through some derivations, you'll be able to obtain that beta equal to r cosine c tau zero divided by d, where c is the speed of sound and d is the distance between sensors. Okay, so this is the I think this is the structure for uh, this determination for the target angle. And then there are other applications which we will just briefly uh, talk about. For example, you receive a waveform acoustic, for example, that speech sounds, and then the speech sound is giving you some kind of share, and you try to determine the parameters in the speech, and also spectrogram type of thing. Okay, so in all these systems, we are faced with the problem of extracting values of parameters based on continuous time waveforms. And due to the use of digital computers to sample and store the continuous time waveform, we have the equivalent problem of extracting parameter values from a discrete time waveform or data set. So mathematically, we have the endpoint data set. So it's a waveform, continuous waveform, and then sampled at discrete time instant. For example, sampled step by step. So you get discrete time samples x0 and x1 all the way to the time index n-1, which depends on an unknown parameter theta. We wish to determine theta based on the data or to define an estimator. What this is saying is the data actually relates to the parameter theta. The x relates to theta. So conceptually, we have to be very clear about this. They are statistically related to each other. Therefore, we will say that the data set depends on unknown parameter. And that's the basis by which we can infer the value of theta from x, right? Think about it. If they are independent, then we will not be able to infer information about theta from x. So that has to be related with each other. And so we define an estimator theta hat as a function g of x1, x, x0, x1 all the way to xn. So where g is some kind of function. So remember that estimator is always a function of something, and it's function of data, data, data. Sometimes we call it observations. So, for example, this is theta hat equal to g of this. And then you may wonder what g is, right? What is the function? That's the problem for the design of estimator. So in other words, that f is to be designed, to be designed. This is something to be designed. So we cannot say for sure yet at this point to say what the function is, because that is the issue we are going to discuss in many parts of the following weeks. So that's for our design. So this is the parameter. This is the problem of parameter estimation. And by parameter, we mean this is continuous. Continuous. This is continuous. This is continuous rather than discrete. If that is discrete, then we call it a detection problem. For estimation problem, the parameter is continuous. Otherwise, it will become a detection problem. For example, we talk about H1 and H0 detection. That is a detection problem. Okay. So with this transition, the estimation problem has evolved into one of estimating a parameter based on a time series. So it's a parameter based on a time series, which is just a discrete time process. So because the amount of data is necessarily finite. We are faced of the determination of G, so this is not set yet. We're going to do the design of G later on. So therefore, our problem has now evolved into one which has a long history. So dating back to Gauss in 19th centuries. Okay. So for some examples, the image analysis, to estimate the position and orientation of an object from the camera. For biomedical, to estimate the heart rate of a fetus. Communication, for example, to estimate the carrier frequency. This is very common. And then for control, to estimate the position of a powerboat. For seismology, to estimate the underground distance of an oil deposit, right? The distance. So those are important questions, important engineering applications. Right? Okay, so now we move to 1.2, the mathematical estimation problem. In determining good estimators, the first step is to mathematically model the data. Because the data are random, so we describe it by its probability density function, PDF, or Px1, x0, x1, all the way to xn minus 1. And then its condition on theta. As we said before, it has to be dependent on the parameter of interest. If they are independent, then we will not be able to infer any information. So this is theta dependent. The PDF is parameterized by the unknown parameter theta. That is, we have a class of PDF where each one is different due to a different value of theta. So we'll talk about this by by the following example. So we will use a semicolon to denote this dependence. As an example, if n is equal to 1 and theta denotes the mean, then the PDF of the data might be like this. So this is a P probability density function of x depending on theta, and then its Gaussian distribution. Okay, of course, the Gaussian distribution is by assumption. We're assuming it's Gaussian distribution, so you have 1 over square root 2 pi sigma square. That is the variance, and then exponent of this x minus theta. This is the mean, right? This is the mean. And then the figure is shown in above figure, which we will see in a little bit, for various value of theta. So let's see this. If you have this distribution, it will look like in this bell-shaped curve. And then it's dependent on this theta. Therefore, if you have a theta 1 in this point, the PDF will look like this. If you have theta 2 here, you have a PDF like this. So it will have located, it will have to be located differently, right? And that's the density for x0. Okay, so let's continue to look at. It will be intuitively clear that because the value of theta affects the probability of x0, we should be able to infer the value of theta from the observed value of x0. So, for example, if the value of x0 is negative, it is doubtful that it could be theta 2, right? The theta 1 might be more reasonable. So let's look. If, let's say, x0 is negative, right? x0 is negative, then x is somewhere around this area. Then theta 1 will be more likely to be this theta 1 rather than theta 2 because the probability falls very low for negative x. And obviously, theta 1 is giving you more probability in terms of negative x0. So the statement is theta 2 is unlikely and theta 1 is more reasonable because if x0 is negative, right? So this is a simple example that gives you a sense of how come x0 is giving us information about theta. If x0, let's say, is here, then we will say theta 1 is very likely to be the true value rather than theta 2. And it's even more unlikely for theta 3 because the probability falls very, very low toward this point for theta 3, right? So I think that gives you a very brief sense of how come data is giving us information about parameter theta. Okay, so we take a break and then come back later.